Hello everyone, so today we're doing a coordinate transformation problem. So a fixed coordinate system is shown. Coordinate system 1 is constrained so that its origin can translate along a line that is in the xy plane of the fixed coordinate system at an angle of 25 degrees from the xf axis. So as you can see, this is the final, and it's being transformed by 25 degrees here. And this is our system 1. So the x1 axis is along the direction of this line. The z1 axis is in parallel to the zf direction. So what we do know is that the ones that are changed from the coordinate system is the y and the x, and it's by the 25 degrees. And the distance of the origin is by d. Now on the other hand, the zf are both parallel, so the direction will be exactly the same. So now the coordinates of point A are given in the fixed coordinate system as P of f of A is 246 meters. So what are we trying to find? We're trying to A, determine the value for the translation distance D. So that point A will lie in the YZ plane of the coordinate system 1. Now, keep in mind the YZ plane, that'll be important later. Now for B, for this value of D, determine the coordinates of point A as measured in the coordinate system 1. So first, what do we need to know? We need to know what the rotation matrix is, as we get from the system 1 to F. So how do we do that first? Well, first, we need to know what the cosine and sine is, as is part of the um, rotation matrix. So what I have here is actually the Python version. As we know, the rotation matrix is having cosine, um, having it in like this, where it's cosine theta, sine theta, and then negative sine theta, and cosine theta. So what I'm using is importing numpy as np. We know the degrees is 25 degrees. So let's just, for numpy, decalculate by radians. So we'll just convert the degrees to radians and put in degrees. So that's our theta. Now, for simplicity's sake, let's call c the cosine theta of the 25 degrees and np the sine theta, which is s. And here are the values that we get. So for cosine, it's about 0.906, and for sine, it's about 0.43 if we round it to 3 digits. Although it will be higher precision when we actually solve the equation. So now that we know this, um, what are we going to do with this information? So first, let's create our rotation matrix. The F1 rotation matrix, it will put in 0.906 and also the 0.423 in this order, just like how we have the rotation matrix. And one thing I just realized is this should be a negative right here. And now you might be thinking, the rotation matrix was a 2 by 2. This is a 3 by 3. Well, since we're working with 3 axes, it would be like this, with the z being 1 as it's not affected at all. So that's our rotation. This is dealing with the 25 degrees. Now, what about the d? So what we want to know is how do we find the origin? We know the origin moves along this d. So what we can do is we know that the origin, especially if we look at the x, is being rotated here by cosine. And then we could calculate the y with sine. So all we have to do is the P1 origin is going to be 0.906, which is the cosine, 0.43, which is the sine, and then it's multiplied by d. Now we have both the rotation matrix and the origin of system 1. So now we can do the transformation portion of it. So the transformation matrix will be composed of the rotation matrix, the origin, and then we're also introducing um, another I guess row, because we're adding in a extra column to the right. This will make it a square matrix if we do 0, 1. So this 0 is actually 3 different zeros. And this is actually it written out. As you can see here, this part is from the rotation matrix. These are all just zeros. And then we have the one here with the origin. Now that we have these two different information, what are we looking for? So what we're actually looking for is from the point A, which lies on the YZ plane of coordinate system 1. Now remember how I said YZ is important? Because it's on a YZ plane, that means X is not affected. If X is not affected, that means it's going to be 0. Now, as you can see here, the only variable I have here is just Y of A1. So Y is 6 determined. 6 is determined from here because Z is parallel. So we know the Z is going to be the same. So we could use 6. So it's going to be 0, Y, A1, and 6. Okay? So now we do the point transformation equation. So the point transformation equation is multiplied from the transformation matrix and also the point of it. So now that we have it together, which we have all the information, as you can see, of the point transformation, we added in 1 here, so to show that it's not affected. So anything that's multiplied by it will be exactly the same. And now our variables are d and y. So what do we do now? What we can do now is actually just multiply the equations. We know if 0 is multiplied through, all of this is canceled out. So let's actually just do that. All of this is cancels out. And then y of a is placed on these two. These are zeros. And then 6 is multiplied here, but those are all zeros. This is where, just like identity matrix, it's going to be 1 all the way through. So for actually our equations, we actually don't even need to worry about this. And then now 1 is multiplied 2 through, so 1 actually does not affect all of these. Now what we're left with is this, and this. And this will give us this equation. So we know 2 equals negative of the, let's see, of the sine. Yeah, 2 equals negative of the sine times y plus the cosine times d. Now 4 equals the cosine of y plus the sine of d. Now we can bring back our Python to figure out the rest. So how do we do this in Python? So what we can do is we already know what CS are since we calculated before. Just like our previous equation of how is negative sine, we could put here negative sine and then cosine and cosine and sine. And this is our A array. That is what we are calling. It doesn't matter what you call it, but I'm just calling it A for the right side, and left side is just 2 and 4, as you can see here. Once we have that, we'll just solve this linear system. This is just an example of what it looks like, and we just use our NumPy linear algebra solve to solve A and B, and we're going to be returning Y and D. Now, from this, we know this is our Y, this is our D, and now just rounding it, Y is 2.780 and D is 3.503. So now we solve our two unknowns. So as I previously said, this is it. And now we know exactly what it is. We know for A was looking for the translation distance D. So we know the translation distance is 3.503. And now for B was looking for the coordinates of point A as measured in coordinate system 1. So the point as in the coordinate system 1, we know it's going to be 0. Yep, right here. 0, it's going to be y, and then it's 6. And we know what y is now, so it's going to be 2.780. And that's how you solve this coordinate frame system problem using both Python and just linear algebra. I hope that helps. Thank you.